So today,
Okay.
Titouan is going to be talking about Flexsymmetry.
Okay, thank you. So I'm very happy to speak about Flexsymmetry because I've been working on this for maybe 2 years now without speaking about it to anyone. So I'm very happy to be able to speak about it now. Before I start, feel free to interrupt me at any time. I really like being interrupted. I really like questions. Don't hesitate to use the chat. I will keep an eye on it. Yes, on the contrary, I'm bored when I'm not interrupted. So please. Okay, so So first, when we look at ZX paper or the graphical language, most of the time at some point, this is mentioned, the only topology matter paradigm, or only connectivity matter, or something else. And basically what it means is that the diagrams behaves like a graph, like kind of graphs. And I know I spent a lot of time with my colleague thinking about when an equation is it true because of naturality of swap, because of Frobenius algebra, or because of compact structure. And it's there is a problem of organizing the equation to really understand what properties come from what. And that's the point of this, is to think about the only topology matter paradigm. So I will say OTM, starting from now, and to say, okay, what really does it mean in terms of equation? So this is what I would call flexsymmetry. So let's see what is flexsymmetry. So we say, first the context, we always assume that we have a symmetric compact structure. Okay, so there is always cups and caps. This is self-dual, so always cups and caps, and they are symmetric. So you can swap their legs, it doesn't matter. So in this situation, a diagram's D from N to M is said to be flexsymmetric if, so first you bend all the inputs into outputs. So you use the map state duality, you have a big state, and then you can mix the legs of the states with any permutation you want. So you have a permutation of N plus M wires. And you say D is flexsymmetric if any way you choose to permute all the wires, it doesn't matter, it's always the same. Okay, so the state you obtain by map state duality is symmetric. So I hope it's clear, because I will say flexsymmetry a lot of time in this talk. So if you do not understand now, tell it. So this is a definition of being flexsymmetric from the diagram. Okay. So is it okay? Do you hear me? Oh, good
Yes.
question. Good question. Okay. So you can hear me. There is a question if ZX spiders are flexsymmetric or not. So let's do some exercises. Okay. So I will just give you some diagrams, some examples, and I wait for you in the chat to tell me if it is flexsymmetric or not. So first is the Hadamard gate. So do you think Hadamard gate is flexsymmetric or not? Okay, yes, for qubits. I said for qubits, Hadamard gate. Yes. In fact, yes, because if you look at the equation, you see you are only on 2 wires, you have only 2 permutations available, and the only non-trivial one is the swap. And in fact, in this situation, being flexsymmetric is exactly being your self-transpose. So being flexsymmetric for one-to-one generator is exactly the same as being self-transpose for the compact structure, and in qubits for matrices is equivalent to have a symmetric matrix. Okay. Okay, so for Hadamard gate, it's okay. For the triangle of delta ZX, so I will call the triangle, the matrix is a 1, 1, 0, 1. Okay, no, yes, no, because the matrix is not symmetric, not self-transpose. Right, in fact. Okay, so this was quite easy. So now the green spiders of ZX. So now we have a lot more legs. So is it yes? Yes, it is, and this is the whole point of the definition. In fact, if you have a green spider, you can mix all the inputs and outputs, it doesn't matter. That's the point. Now the black spiders of ZW. So ZW is less well known. So Okay, yes, in fact, it is the same. And the Hadamard boxes of ZH. Okay, depends on your definition. We will see this later. Yes, the Hadamard boxes, they are also. So this is the point. So all the three languages, the main interest is that they are flexsymmetric. Okay, and now more difficult, the fermionic swap of the W, or it also works for the regular swap. Same question, in fact. And yes, the answer is no. Yes, that's exactly okay. So the answer is no. I see I need to say out loud what's happening in the chat because this might not be recorded. Okay, so someone say no, only up to cyclic permutation. And that's right. In fact, you can weaken flexsymmetry and say you only allow cyclic permutation. And yes, the swap and the fermionic swap will satisfy this weaker property. But here in this talk, I will just speak about flexsymmetry and not flexcyclicity. And finally, the white spider of graphical linear algebra, of interacting Hopf algebras. So does anyone has an idea?
Does it depend on what cup or cap?
Yes, exactly. That's the point. It depends. It depends which compact structure you choose, because you have two compact structures available, two natural compact structures available in graphical linear algebra. And I think there's the authors never really choose. So if you take the white compact structure, it is flexsymmetric, but if you take the black compact structure, it is not. Okay, so now I think we are very clear about what is the meaning of flexsymmetry. So what does it mean for a language to be flexsymmetric? The idea is to organize your equation and generators between an implicit part and an explicit part. Implicitly, when I say flexsymmetric graphical language, I will always have some implicit generators, which are the cap, and the swap. Okay, we're in a prop. And those generators, they will always implicitly satisfy all the equation we expect. So we have a compact structure, it is symmetric. We have the swap is an involution, and you also have the naturality of the swap. You can always make your diagrams go through the wires. And you also have implicit equation stating that all explicit generators are flexsymmetric. So I hope it's clear. And then you have the explicit part. So then you have some explicit generators. And then in a flexsymmetric graphical language, you always require them to satisfy the flexsymmetry equation, okay? That's the whole point. And then you also have explicit equations. And in those equations, you have the right to use, of course, explicit generators, but also implicit one. You know, you assume they are there. So the caps, and the swaps, you can also use them in your equations. This is allowed. So this is the definition of a flexsymmetric graphical language. So each time from now on, when I say flexsymmetric graphical language, this is it. We have a cap, we have swap, and all generators are flexsymmetric.
This one?
Yeah.
I'm a bit confused because you say all explicit generators are flexsymmetric, and you also say explicit generators that implicitly satisfy flexsymmetry. Like, is that?
It's like no. Don't be confused by this. I just mean that the fact that the explicit generator satisfies flexsymmetry, okay, I will not write it. This is what I mean by implicit, okay? It's just explicit is just what I will write, what you will see, and implicit is what I will just assume.
So in this talk?
In this talk. And this is my definition of a flexsymmetric graphical language, okay? Okay, so now I will give some example. Maybe it will be clearer. Don't hesitate if you have some question. Yes, do you have some questions here? Or is it okay? Do you see the point? Okay, I have no answer, so I take it for a yes, which is a very bad thing to do. Okay, so let's look at an example. So here is the flexsymmetric graphical language of monoids. So you see, you have so I think you know this. You have the unit, you have the multiplication, you have the associativity equation, and you have the unit equation, the unit rule. But this is a FLEXSYMMETRIC graphical language. So you also know that you have a cap, you have a swap, and those two generators, the unit and the multiplications, need to be FLEXSYMMETRIC. And it might be easy for some and not for others, but in fact, a FLEXSYMMETRIC monoid is exactly a commutative Frobenius algebra. So I don't know if is it clear for everyone, or do you want more explication on what is it true? That if I just say the explicit part, just usual monoids, and if I am in a FLEXSYMMETRIC setting, then I directly have a Frobenius algebra commutative. So at least it makes sense to one person. So we'll see if, so let's assume this for now. And in the question, if you want more explanation, I can give you different intuitions. One intuition in that you see you have a monoid, then you can use a cap and cups to turn everything to obtain a comonoid, because you also flip all the equation. And then to obtain the interaction between the monoid and the comonoid, you see that taking the associativity equation, if you just bend one leg, you are able to recover the usual interaction between monoid and comonoid in Frobenius algebras. And it is a well-known fact that, in fact, Frobenius algebras is kind of just associativity in all direction. Okay, so this is a FLEXSYMMETRIC monoid. So sometimes we are not lucky. There are generators or diagrams which are not FLEXSYMMETRIC. But if we are lucky enough, they can be close to that. They can be FLEXSYMMETRIC up to dualizer. So what does it mean? It means you have a dualizer, which is a FLEXSYMMETRIC involution, one-to-one. So remember, FLEXSYMMETRIC for one-to-one is just a self-transpose. So you have such an involution, and if you plug it on top of your diagram, then you satisfy FLEXSYMMETRY. Okay, so this is the point of being a FLEXSYMMETRIC up to dualizer. And in fact, in this specific situation, and we will see it happens quite often, then we can change our graphical language. And what we do is that instead to say that D is a generator, we said we have a new generator D prime, which is defined as being a D with some dualizer on top of it. And then we obtain a FLEXSYMMETRIC generator. Is it clear? Does it make sense? This idea that I can redefine new generators that satisfy FLEXSYMMETRY in this specific situation. So it will be clearer, I think, if we take some example. So what's happened if I have a monoid that is only FLEXSYMMETRIC up to dualizer, and I do this trick? I say, okay, I will redefine it, twist the language a little bit, such as the involutions, the dualizer are implied. Then you modify all the equation and you obtain this. So this is what I'll call the subdivided monoid. And if you are familiar with ZW, you already have seen this kind of equation. In fact, they are very, this kind of patterns are very typical of ZW. Because in fact, a subdivided monoid under FLEXSYMMETRY gives you exactly something that behave like the black spiders of ZW or the Hadamard boxes of ZH. It is, they have been called parity spiders or pseudo spiders. Me, I call them harvestmen. But that's exactly this. And in fact, you see, you have a point of view on the Hadamard boxes is that they have been obtained by subdivided a monoid. So I think it's kind of known that if you start with the monoid, the AND gate, so you have a monoid. And this AND gate, you have a monoid, but this monoid is not FLEXSYMMETRIC. But it happens, this kind of mysterious, that it is FLEXSYMMETRIC up to dualizers, and the dualizer is exactly the Hadamard gate. And then if you apply the softening trick, you redefine your AND gates to put this Hadamard gate on top. And this is how you obtain the Hadamard boxes. Oh, there is a mistake here. This is you obtain the Hadamard. So this is the point of view on the Hadamard boxes of ZH. That's in fact what you did is to force the N monoid to behave nicely with respect to the cups and caps. So this is the point of it. We'll see later if we can have this kind of point of view. Oh, why I call it softening? So you need to remember that English is not my native language, so I can also do huge mistake by choosing my words. Softening for me because you have this idea to soften in the way you make it more flexible. Like yeah, maybe relaxation. I should find maybe another name. I'm not sure it is exactly the meaning of it in English. Might be a mistake. Okay, yes, and we'll see what's happened if we take this point of view on CW. It's more disappointing. Okay, so now for now on, I will just give you a lot of examples of FLEXSYMMETRIC point of view of non-graphical language. So I will first start by graphical linear algebra. So in graphical linear algebra, a map from N to M is in fact a relation between N tuples and M tuples, okay? A map from A to B is a relation between A tuple and B tuple that have to be, linear in the sense that if something is related to another, then if two things are related to another, then the addition, the sum should also be related, and you can also multiply by a scalar and the relation still holds. Okay, so very natural linear relation. Okay, so let's see. We have two spiders here. We have this black spider. What it does is that you need all the tuples to be the same, always the same x. Okay, so this is very, very close to the green spider of ZX. You require the x to be the same everywhere, on every legs. And you also have a white spider. And this white spider is defined like this. You have a tuple x is related to a tuple y if and only if they sum to the same number, okay? So again, this is also close to the red spider of ZX in a way. And in this language, you have other things. You have this red box, and you see just take a minus sign, okay? It's x and minus x. And if you look at the cups and caps, so the swap is kind of obvious, I think. If you look at the cups and caps, you see they correspond, in fact, to the black spider, okay? They are just the ternary black spiders. The zero is the empty tuple. So, of course, the black spider will be FLEXSYMMETRIC with respect to this compact structure, okay? It's a native black compact structure. But what happened with the white one, we see, in fact, if we want to use a compact structure to switch an input to an output, what's happened if we take a y here and we want to take it to the other side of the equality sign, then we need to add a minus, okay? It's not possible to keep it this way. We need to add a minus. And this is exactly what will happen. We will need to use these boxes here, this box, this red box. So in fact, we see that the white spider, with respect to this compact structure, is not FLEXSYMMETRIC, but it is FLEXSYMMETRIC up to dualizer, and the dualizer is exactly this red square. Okay, I hope this is clear. You see the intuition that here you have an asymmetry between the inputs and the outputs, and if you want to transform an input into an output, then you need to put a minus, okay? So you can use the softening trick, and the idea is that you will have a new spider, which is not a regular spider, but a parity spider of harvestment, something that behaves like the H boxes, which is defined like this. And when you look at the semantics, you see exactly here what happened, that we managed to have back the symmetry between inputs and outputs. In fact, we just take all the y and we put them at the same sign of the equal sign, on the same side of the equal sign. Okay, I hope I'm not losing everyone with this consideration, but the idea here that we really we are already now able to have a FLEXSYMMETRIC language. And what is very nice is that now when I state what is graphical linear algebra, I can also rewrite all the equation up to FLEXSYMMETRY. So here you have a complete language for linear relation. So it's not impressive if you don't know graphical linear algebra, but usually the language is presented with a lot of more equation because you have to take into account all the possible way to swap between inputs and outputs.
So is this is only in the case of like finite fields? Or?
Okay. So when you look at the most mysterious equation is the family of equation you see at the right here with the k's. Here, a k means that you have k wires in parallel. Okay, so k wire connected here. In fact, this axiomatization is good for any. I think it's my this axiomatization is good for Q. This I'm sure. If you're working with
FP.
Z over PZ,
yeah.
I know you can do better. I'm not sure for any finite fields. I think you have a finite number of equations, but I don't know if exactly this one.
I mean, like prime order finite.
Yeah, prime dimension. Yes, this will be. You can even have a finite number of this equation, and you can even do better. You can only state that if you have a k wire in parallel, they cancel. It's kind of a generalization of the Hopf rule, which will just state the characteristic of your field. And you can, in general, for general fields, you just need, instead of those construction with k wires, you will need to replace it by some boxes. But this is kind of a technical graphical linear algebra stuff. But you can just see that for, remind that for Q, for rational numbers, this axiomatization is complete. Yes, correct me, Cole, if I say something wrong about graphical linear algebra. Okay, so yes.
Titouan.
Yeah.
I see that you have a bialgebra equation. Does that mean in the original axiomatization, the bialgebra equation had some of these red boxes there?
Which this is very nice here. In fact, maybe there is an equation missing. I don't know. Oh no, okay, no, it's technical. Okay. In fact, the point is that in this situation, the dualizer, they are also copied by the other spider. So you're right, in general, I should add some dualizers, but in this very specific situation, it happens that using all the rules, I can show that it is equivalent to put some or not put some. Is it clear?
No, I'm more surprised that the equation now looks really clean, but it sort of seems to mean that in the original equation from general graphical linear algebra, you should have some extra boxes there. Is that correct?
What's up? Yes. In fact, in graphical linear algebra, you have this red box here. And here the box is hidden into the new spider, in fact.
Also in graphical linear algebra, the boxes like can be derived from.
Yes. This was already known. If you go to the blog of Paweł Sobocinski, graphicalgebra.net, you will see there is something. They already knew that they were able to get rid of this this red square here. And what I did, in fact, the only things I did here is just recover to obtain something more compact. What I did here, just take the axiomatization without the red square, and then I added FLEXSYMMETRY. So I said, okay, all those equations, they are equivalent up to FLEXSYMMETRY because you just transform some input into outputs, and that's all.
Where are the faces? I mean,
sorry?
Where are the faces?
Oh, in graphical linear algebra, there are no faces.
Then how can you represent any matrix?
Oh, so in graphical linear algebra, you saw the semantics is not into vector spaces. It's linear relation. It's something, and the tensor product is not tensors. It's the direct product
of
relation spaces. It's the sum. So in fact, this is a kind of weaker. You have less spaces, less space in a graphical linear algebra. So it's kind of easier to obtain completeness. Okay, you need less or universality.
Okay, thanks.
Yes, point is mainly universality. But we will see what we can do with faces. because now something more interesting for you, I think that we'll do a FLEXSYMMETRIC qudits, ZX-calculus. So here, the green spider is as usual, just equality. You ensure that inputs are equal to outputs. And the red spider, like in ZX, we ensure that the sum modulo D of all the inputs is equal to the sum modulo D of all the outputs. So this is my definition. And then the compact structure corresponds to the compact structure of the green spider. Okay, it's equality. The swap is kind of obvious, I think. And here what's happened that we see is very similar to the previous result, that in fact, green is obvious FLEXSYMMETRIC because there is a complete symmetry between inputs and outputs. But the red one, you see, if you want to transform an input into an output, you want to go to the other side of this equal sign. And then you need to put a minus. And in ZX, you don't care about it. Why? Because we are modulo 2. And in characteristic 2, -1 is equal to 1. So this is why ZX is by accident FLEXSYMMETRIC natively. But qudits ZX-calculus is not. Now you need to take into account this minus. But we see also that what's happened, that in fact this red spider is not FLEXSYMMETRIC, but it is FLEXSYMMETRIC up to a dualizer, which is exactly taking the minus, okay? The minus modulo D. So we can define, using the softening trick again, we can modify this red spider, and we do exactly the same trick. We will just take all the outputs and we put them to the other side of the equal sign, okay? And now we have something behaving like the spider of the W or the H boxes, but which now it's FLEXSYMMETRIC with respect to the compact structure. And what is more fun with it is that if you define the Fourier transform, I hope this is true, but yes, I think it is. If you define the Fourier transform for qudits, then you have this relation. So it's not easy to see directly because it follows from different facts. The fact that this minus generator that takes the minus modulo D, it can go through through all spiders, and the fact that the inverse of the Fourier transform is exactly the Fourier transform times this minus generator. So you can define a Fourier transform. It will not be an involution. It will be of order 4. And if you put together two Fourier transform, you just obtain one red node of this new spider. So this is a nice way, I think, to present qudits ZX-calculus. The only problem that then you have to kind of learn again ZX-calculus, because a lot of equation you used to, you win some topological advantage, but then you have to take care of this ZW-like spider. Okay, so here example of some equation that holds in this setting. So here I do, oh, sorry, I forgot the phases, but so here I do not claim for completeness or universality. If you want completeness, you can take the paper of Arnie and then try to see if you can you can change all the red spider by this one, and then quotient all the equation by modulo FLEXSYMMETRY. I did not do this. I need to do this at some point. And if you have phases, you can also put some phases. The only difference that when you fuse two red phases, now you will need also an involution between, or you are not able to add the phases. And usually, for example, in qudits, ZX-calculus, the phases, you have a tuple of phases. And this, in fact, corresponds to, if you take just a phase or a phase when you compose with involution. So again, this is technical, and I did not. Yes, it's not the right slide. You know, you should have more equation to really understand it. By just by speaking is not easy. But let's. Yeah.
I have a question.
Yeah.
Where does like the dimension come in here?
Oh, so you see what look like the Hopf rule here
Yes.
in the middle? You see, this is the Hopf rule. This is really the Hopf rule because you have an antipode. You have the involution here.
Don't we need like, don't you need some rule like if you like copy and then add things like d times, then that's the same?
Yes, exactly. The point is that this Hopf rule is equivalent to stating that the characteristic is 2 in ZX-calculus. But in qudits calculus, those two facts splits. So you have the Hopf rule, but you could also add another rule stating that if you, for example, for qudits, you could have a rule stating that 3 wires just cancel.
So is this is just for qubits then?
No. In fact, those equations, they are true for all qudits. Okay, but this is clearly not a complete set of equation.
Oh, okay.
You should add other equation. No. It's possible, I think, to obtain something complete if you take the calculus of Arni and you try to modify everything. And then I think there are triangles in this axiomatization. So you should also take care of the triangle to make it FLEXSYMMETRIC, which is possible. It already has been done for delta ZX for a reason I will tell later. Okay, so what happens
wait,
now?
sorry,
Yeah.
Titouan, could you go back for a bit? Why is there a swap in the bottom? I thought everything was symmetric.
Oh, yes. In fact, because of FLEXSYMMETRY, putting the swap here doesn't matter completely. It's just that I took some slides I already did for the FLEXSYCLIC case. And then you could have the same kind of language, not for qudits ZX-calculus, but for any group ring, even for non-commutative groups. And then this swap would matter. This is exactly the fact that if you take the inverse in your group, you see you have A time B, you take the inverse, this is B minus 1 time A minus 1. You change the A, B. Here, it doesn't matter because the group is commutative.
This is like in Sean's talk, like a few weeks ago.
Yes, I was not able to be here, so I should look at the recording. But yes, and in fact, people like Shane doing Hopf algebras and the kind of things. Usually, the equation with the antipode takes this form with the swap, or even a braid if you are completely crazy. Okay. It remains 2 examples. Sorry, I'm a bit long, so I promise only 2 examples remaining. What happens if we look at the W and we say, okay, the W is weird, but just because we try to force the black spider to behave in a way that it doesn't want to. So maybe we just force the things in a way that the black is FLEXSYMMETRIC. What's happened if we relax this condition? So what do? We just do kind of the reverse reasoning. So we will define 2 new spiders by adding some involution, okay, to the black spider. But remember, so here, follow me. The black spider is FLEXSYMMETRIC for the usual compact structure. Now we are adding involution on it. So clearly it will not be FLEXSYMMETRIC anymore, but it will clearly be FLEXSYMMETRIC up to involution, of course, by definition. So here the idea is instead of changing the generator now to recover FLEXSYMMETRY, I will change the compact structure. And I will put the involution in the compact structure, hide it, and then I will have FLEXSYMMETRY. So I hope it's clear. Don't hesitate to interrupt me. So here you see, I define those orange and indigo spiders. And to do that, what do? I just take the black spider and I put the dualizer on top and at the bottom. And then you see the semantic of the compact structure is different. Okay, in fact, it's a compact structure with a NOT gate. Okay. So you see the semantic of those things. It's completely unnatural, the semantics. So I really are disappointed of what happens when you do this to W. But there are some nice things. You obtain this kind of equation. So instead of parity spiders, you recover normal spiders. And they are anti-spatial. So this was already known. And then you have all those equations, which are, I think are kind of nice, but here what we did is really to split the black spider of ZW into two spiders. So here I'm not speaking about the white spider, and as we said already, anyway, the fermionic swap does not behave well with respect to the compact structure, to any compact structure, in fact. So this does not give a good presentation of ZW, I think. Just interesting to see that the black spider can split using the same kind of reasoning. And it's also interesting because this idea of changing the compact structure paves the way to my last example, which in fact I already presented maybe 2 years ago, 3 years ago in Grenoble, I think, is what happens if you take the ZX-calculus and then you perform this. You add an Hadamard gate on the top of the green and you add Hadamard gate at the bottom of the red, and those two happen to be the same. And this is what I will define as my new monochromatic spider. And in fact, remember, the green and the red for qubit ZX-calculus are both FLEXSYMMETRIC with respect to the usual compact structure. So now I just added some Hadamard gates here. So clearly it will not be FLEXSYMMETRIC. It will be FLEXSYMMETRIC up to dualizer, with the dualizer being the Hadamard gate. So what I will do to recover FLEXSYMMETRY, I will change the definition of the compact structure. So you see the semantics here of the compact structure is a usual compact structure plus an Hadamard gate. So here I change the definition of the compact structure, but now I have a FLEXSYMMETRIC graphical language with only one spider, which is a parity spider, a spider of ZW, okay? And then you can obtain a monochromatic ZX-calculus. So this is complete for qubits. You just take one parity spider and you enforce this equation and FLEXSYMMETRY, and this is complete for qubits. So this is my last example. I think it's I don't know if it's useful because it's very difficult to use this language. For example, the fact that the compact structure has not the same semantic as before is very strange. So I think it's quite beautiful to see you can axiomatize qubits with only one spider. Okay, so that's all. I have no more example. So the main question is, why caring about this? In fact, I really care about this, not only because of OTM, but because of graphical proof assistance. In fact, I know that when people try to implement the delta ZX into quantomatic, it was not possible because of the triangle. And why? Because the triangle is not FLEXSYMMETRIC, in fact. Because in PyZX, I think it's the same also. The implementation is done in such a way that you can only implement FLEXSYMMETRIC graphical languages. So that's why it might be interesting to have some methods to turn non-FLEXSYMMETRIC graphical languages into FLEXSYMMETRIC graphical language. Then there is a conjecture I have that in fact the free FLEXSYMMETRIC graphical languages are correspond exactly to a category of labeled graphs, in fact. So this will be kind of the coherence result that ensures that FLEXSYMMETRY is a good definition of only topology matter. I still need some work to prove it, but it's close. It's close. I believe in it. I think I have a good definition of a category of labeled graph to do this. There is this notion of implicit versus explicit. In fact, I applied it to FLEXSYMMETRY here, but it's more general. We could find also a nice set of implicit equation and implicit generators that could lead to other paradigms and maybe to other implementation in other graphical proof assistance. So this is something I kind of really believe that you have a kind of duality between those paradigms and nice implementation and graphical proof assistance that allow you to use a rewriting strategy and stuff. Okay, and finally, just a warning. So there is something on arXiv about this, if you're interested, but it's refused. It's a rejected leaks paper, and it was rejected for good reasons. There are false claim and false proof in it. and I had no time to correct it yet. So if you find it, be very cautious, okay? Be very suspicious of everything. Nothing is completely infixable, but I need to take care of it, and I have no time to do it yet. So if you have questions about it and you are interested, the best is to ask me directly in any way, or just right now. So thank you very much for your attention, and I'm staying here to answer your questions.
Well, let's thank Titouan. I have a question.
Yes.
Slash comment. Are you aware of like this thing that Amar observed, how like algebras can be seen kind of as in 3 dimensions in
Yes.
like, yeah, so like in this paper, for those who like aren't aware, there's like a algebra can kind of be seen as a sort of isotopy in like 3 dimensions, where the multiplication is in one axis and the co-multiplication is the other axis. And then if you have like interacting Hopf algebras, then because you can get the antipode from like composing like the red cup with the green cap or whatever, the white cup with the black cap, then the antipode can be kind of seen like a twist in 3 dimensions. So like, I'm wondering if this, I forgot what you call this FLEXSYMMETRY with this antipode added, if this is some sort of like projection, 2-dimensional projection of some 3-dimensional isotopy, or if you thought about that.
Clearly, no. Yes, I've seen this fact before, that the algebra is very natural in 3 dimensions, because you will directly see how does it connect and what happened. No, clearly did not thought about this.
Because maybe that might explain why like this is so natural. If like this is actually some 3-dimensional sort of thing that you're like recapturing in like 1 dimension lower, like you're like discovering some high dimensional thing by its projection, perhaps. So maybe that's just a comment. I don't know.
A side comment.
Maybe.
A side comment to this is, and a question: when does this fail? When can you not do this?
Oh, it's a very good question. In fact, so we thought about it, because all the examples we know, it seems we're able to give a FLEXSYMMETRIC presentation. But in fact, most of the time, it's not possible. For example, if you take the free prop over some generators, it will clearly not be possible to find a FLEXSYMMETRIC axiomatization. And in general, if your prop is too free, in the sense you have, for example, just take any prop and add 1 generator with no other equation, and then you will not have FLEXSYMMETRY, for example. So most of the props, I think, and I'm quite sure of it, it's not possible to find a FLEXSYMMETRIC axiomatization. What happened that we were very lucky, usually the prop we work with, like linear relation or matrices, vector spaces, seems to be very well behaved with respect to this property, and it's possible to fly FLEXSYMMETRIC axiomatization. I hope I understood the question well, and I'm not answering completely something else.
No, I think you understood the question. I need to put the answer in the context of what I know, but thank you.
Yeah, again, it's kind of easy to say, take any prop and just add 1 generator, and of course it will not satisfy those equations, because they are equations, and if you have something freely, it will not satisfy equations. It's kind of a very easy and disappointing answer, but it gives you a counterexample.
So this generator that you might add,
yes,
is it redundant or not? Do I get the idea correctly?
No, you added what do you mean by here? I'm on a completely theoretical level. I just say I add 1 generator, so it will not be redundant by definition, because it obeyed no equation. To be redundant, you need to obey an equation with respect to other generators.
Yeah, okay, I see.
Yeah,
okay.
This is purely a theoretical answer, but this is an answer.
Okay.
Is there any other question?
Titouan, I just want to remark that I'm really happy with the example you gave of qudits ZX, because that's bothered me for quite some time, that you lose the symmetry for the red spider in the qudits ZX. And I was wondering if there was a solution like this. And the solution I had in mind was as well to take the Z spiders surrounded by Hadamard. So I'm very happy that you found the same solution, that it works well. You get like a similar set of rules.
Yeah,
So,
again,
yeah,
this the part on qudits need to be checked a little bit more to be really, really sure if everything works nicely. But the idea is good, I think.
I have a question, another question. So like, there's this relation between linear relations over FP and like qudit ZX calculus. So like if instead you like looked at like linear spans instead of linear relations, so that like the one Frobenius algebra isn't special anymore, then like this can be interpreted as like the phase-free qudit ZX without the Hadamard gate. But in the one on the linear relation side of things, you like you compose things with the antipode, but then on like the phase-free ZX qudit thing, then you compose things with the Hadamard. So like, why'd you make the choice to like on the one side have the Hadamard gate and on the other side have the antipode? Like if linear relations like lives within the qudit ZX calculus,
Yes.
like why could you not do the same thing with -1 instead of with the Hadamard gate? Or
Okay, you mean okay? Yes, I see the.
if you understand the question, it's
Yeah, you mean okay. So yes, I understand the question. So let's try to answer this. Here, my goal was to keep the same compact structure as before. And yeah, I hope what I will say is correct. Okay, yes, my goal was to change the language, to be the more conservative as possible, if you see. And the whole point is that, in fact, this antipode, the minus in modulo D, behave very well with respect to the other spiders. For example, you just go through the green spider and also just go through the red spider. So this is why the equations are not very different. And what's happened if I take do the kind of same tricks with the Hadamard gate? I'm not sure I completely understood your question, because I think you obtained something very close to the monochromatic case.
oh yeah, I think I just misunderstood the slides. So the qudit ZX calculus, are you doing like almost the same thing as for linear relations?
Yes, clearly. In fact, oh yes, this might. If you look at this slide, you see in the Hopf equation the antipode here. In fact, this one is defined by setting ket x to ket minus x.
Okay, so this is like almost the same.
Yes, this is really, really close. And in fact, your understanding of the link between linear relation and qudit ZX calculus might explain why this is so similar, because the trick is exactly the same. Remember, I exactly gave the same explanation about putting something to the other side of the equal side.
Yeah, I think you would get the same if you just took the thing that you did for linear relations and then you just relax the condition that one of the spiders need not be special. Then you would get a complete presentation for the phase-free
qudit
qudit, yeah.
Réponse?
Yeah.
Maybe. No, I don't. No idea. Should try.
I think so.
Try and see. Should try and see. Is there any other question, or do we end here?
Do you think there's any way you could recognize whether a prop has a FLEXSYMMETRIC presentation or not?
A good question, but the only counterexample I have are easy because they are just kind of free props. Okay, it's very easy to say this is not. In general, it is very hard to prove that something is not possible.
Mm-hmm.
Say if I need to find a kind of an obstruction to say no, this will never be the case. And I don't know. The thing is that compact closed category, in fact, I don't know a lot of them. And and the one I know seems to be axiomatizable in a flexsymmetric way, but I have no general proof of this. I don't know. Relation, maybe. I don't know any complete axiomatization of relation. Maybe there are some. It is not possible.
Of relation? What do you mean?
Really a relation over sets.
Like with respect to which tends with the direct sum?
Okay, yes, that's a good. No, using products, I think. Yes, so Cartesian product.
Well, then it's no longer a prop
Mhm.
because yeah, it's no longer a prop because you have to fix a base.
Sure.
You say you have to fix a base.
Because you can have like different like
No, you need to fix a set, you mean?
yeah, you have to fix like
yeah. Okay, but let's say this: you fix a set and you have a relation. I don't know. Maybe there are sets.
I have a complete axiomatization for the two element set.
Okay, and is it easy?
Relatively easy.
Okay. So, and is it flexsymmetric?
No, because you have like an AND gate, but you don't
Okay.
have a Hadamard
Yes,
gate because there's
and you
no
have no Hadamard to.
the
so
Fourier
maybe-
transform isn't.
In fact, I think. Okay, so maybe relation over two. Maybe it's not possible. I don't know. Maybe this is not possible.
Yeah, because it's almost like the ZX-calculus, but you don't have the Hadamard gate. So
Yeah, you don't have this miracle.
Something that doesn't work.
I know we have tried this at some point just with the AND gate. We looked at how we could make the AND gate more flexible just inside a relation. And we convinced ourselves that it was not possible, but it was not a real mathematical proof. So I don't know, but I would not be surprised that, for example, relations it's not possible. Maybe the language is it's too free. This is my intuition, that if you have something that is too free somewhere, then it will not be possible to.
I think at some point in a draft for a ZH completeness paper, we had a remark to that effect that you can't make the AND gate symmetric inside this classical context. But I think we removed it because we didn't have a proof. So if you have a nice proof of it, it might be nice to be able to refer to it in the paper.
Yeah, it's very incredible that it happens that if you want to make the AND gate behave well, then the dualizer is exactly the Fourier transform. And this also happened with in qudits with D prime. If you take the multiplication, then the Fourier transform, I think, is also working. And it's very mysterious for me. I don't really understand why. Okay.
It seems like it's some property that you can factor. You can like split things, like what do you call it, like softening. Like if you can't soften, then like if you can't factor the thing into like smaller parts, then
Yes, kind of. And the problem that you're factoring into smaller parts, but one of the parts is invertible. So it's always difficult to speak about.
It's like a lifting or like
or yeah, just rewriting it in other bases more. Those kind of things. It's not really decomposing. So.
I mean, you could argue that the same kind of decomposition for the C knot is what results in ZX-calculus, because there you decompose C knot, but then not in the same wire, but like a cross wire, sort of.
Okay, but yeah, on a general point of view, I agree that the main interest of ZX is that you have some very rigid gates, and you were able to decompose them into smaller components that are behaving good on a topological level, that are more flexible.
That makes me wonder, actually, like, is there a way we can decompose the AND gate like horizontally, like across the inputs, like in a similar way to the C knot? Like, or does that not make sense at all?
Then you need a triangle, right, to decompose AND gate.
Oh yeah, I guess a triangle does that. Yeah.
I think the thing that fails about relations, or even like multi-relations, is that you don't have like -1, so you don't have like some kind of underlying antipode kind of negativity lying around, and that's like what you seem to be using a lot here.
No, I don't know.
Like
I think we can continue to discuss, but maybe allow the people who want to leave to leave.
I have another question too.
Okay. So you have another question.
Yeah, if people want to leave, they can leave. But
Okay.
we're still within your time.
No, it's okay. In 1 hour, someone will kick me off my lab because of coronavirus situation. But I still have 1 hour. So me, I can stay 1 hour. But yes, feel free to leave if you want to leave. I don't want to.
You have this conjecture. At the
Yes.
end, involving like labeled graphs.
Yes.
Is this notion of flexsymmetry with the antipode or without the antipode that your conjecture is
My conjecture is that, okay, so what is very nice with flexsymmetry is that it obeys this pattern of explicit and implicit, okay? So this allows to define what does it mean to be a free flexsymmetric language over generators. Because you have some generators, okay? And then what is the free flexsymmetric language is you take the generators, you add the implicit generators, you add the implicit equations, and that's all, you're done. So this gives you a notion of free flexsymmetric graphical language. In fact, you can even show that you have a flexsymmetric monad over the, yes, a monad over a signature of props, that you have a monadic adjunction that allows you to talk about the free flexsymmetric graphical language. And then the conjecture is to say, okay, but what is a free flexsymmetric graphical language? And I think this corresponds to a category of label graphs I designed. The problem with this kind of proof that it's very hard, just for me to tell where it is rigorous enough. I don't know if you see what I mean, that you say, okay, this is clearly the same, but how much clear it is. And I really need to think of what kind of tool using, if I need to go back to the Rock of Street and Joyol, or maybe I can use the thing of Alex, or I don't know.
I guess there is no notion of like free, what's it called, like softened, relaxed, like flexsymmetric graphical language, because the antipode relies on
Oh, you mean, okay, yes, you mean the flexsymmetry up to dualizer, for example.
yeah, so that there's no free notion of this.
No. My idea is really that you could, but my idea is really that, okay, flexsymmetry is really the notion you want, is a nice notion, but sometimes you don't have it, and then you look if there is way to twist the language a little to recover it. And one way I found is this notion to say, okay, if you are flexsymmetric up to a dualizer, then I know what to do to recover flexsymmetry. But for me, this is really not a notion itself, flexsymmetry up to a dualizer. It's just something that a situation when you say, okay, I'm not in a good situation, but I can twist my language a little bit to be in a good one. I don't know if I'm clear, but I never thought, I think it would be completely, for me, this conjecture is a point in proving that flexsymmetry is not ad hoc. So flexsymmetry up to dualizer would be even more ad hoc.
Yeah. Where do the labels come from? Like, is your intuition for?
So I feel very stupid because I did it. I did it by hand. You know, I just say, okay, you have some graphs. The vertices, they are generators. So you have different kind of vertices. Their arity are fixed of those vertices because they correspond. Then to need some inputs. So you have some open graph with inputs and outputs. Then you have some problem with the loops. So you need to take care of them. So I did it by hand. And at some point I discovered, it was pointed to me by a reviewer that in a paper, I don't remember exactly the paper, a paper by Miriam and some other people, they gave exactly the definition of what I call a label graph. It's just that they say, this is a definition of only topology matter. They say the two diagrams are equivalent if the corresponding label graphs are equivalent, are isomorphic. So in fact, they already had this definition of label graphs, but then you need to define how to compose them and to tensor them to have a proper category. And this required a little more care.
Interesting.
And but this would be really, yeah, I will have, I think I will have it at some point. Just need a little more work.
Interesting talk for me, especially.
If no one else has a question, I want to say I'm intrigued by the monochromatic ZX.
Okay.
Like, I think you posed the question how useful it is. So why shouldn't I use this instead of the normal one? What looks ugly in this one?
What looks ugly, you mean? Oh, because I say that I don't like to use it. In fact, I don't find it is ugly because I find it very beautiful and elegant to be able to have a complete language with just one family of generator. And
So,
also the equations are not so ugly, in fact. You see, okay, the problem that what is very nice with ZX-calculus when you use it is that, in fact, this kind of close of the usual way you do matrices. For example, you want to do the transpose of a matrix, it's very easy to draw it in ZX. Things are kind of natural. Here, your compact structure is really unnatural because there is a Hadamard gate coming in. So each time you want to just, you want to turn upside down something, in fact, you are conjugating by Hadamard gate. This is not usual. And the generator, it has no nice interpretation. You know, the green spider of ZX and the red spider of ZX, they are very, very nice interpretation. You really understand what's happening. And this new generator seems, you see the semantics, it's strange. At least me, I have absolutely no intuition about this language.
So, okay, this is something that confuses me. So I thought that the point was that this is FLEXSYMMETRIC.
Yes.
So you don't care about what is input, what is output. It's a graph.
Yes.
But then you tell me, oh, if I want to bend wires, then it's annoying because it's weird. Because there's a Hadamard thing.
Alors,
but
in fact, yeah, so.
You see, right?
Yeah, I see the problem. So, yeah, it's just, so it's coherent, don't worry. So what I'm saying is, yes, it is FLEXSYMMETRIC in the sense that the equalities, the topological equality you are used to in ZX are okay. So you can move wires around, everything works. What I'm saying is that what used to be easy to understand in ZX, for example, what is the meaning of turning a diagram upside down? You say, okay, if I have a matrix, I just take the transpose of the matrix. And what's happened here is that you lose this clear connection with the semantics. So you have a connection, but it will do something weird that you are not very used to. In real life, it's very, no one takes the transpose of the matrix and then conjugate that Hadamard. It's not a native operation of linear algebra like a transpose here. Do you see my point? This is what I mean when I say it's weird or it's...
Yeah, okay.
It's not on the syntax is very nice, but the semantics is ugly. That's the point.
Okay, sure.
I have another question to kind of give me an intuition about your conjecture. When you consider like the free FLEXSYMMETRIC category on a monoid, or
yeah, I can give you intuition. Okay,
but like, is it you don't even need? Is it true that you don't even need like the unit or the associativity? Like, does this follow from? Or no, if you just have if you have the free FLEXSYMMETRIC category on like a generator like of arity 2 to 1.
yes.
Like, is this a Frobenius algebra or is it?
No, you will need the unit, of course.
Okay, and it's not associative.
And yes, and you need associativity. In fact, okay, the intuition is that, for example, take a generator 2 to 1, okay, and you take the free FLEXSYMMETRIC graphical language. What happened that if you take your diagram you can draw boxes around your generator. And what you see is that thanks to the FLEXSYMMETRIC equation, you can, yes, you can use map state duality, okay, using cups and caps. So you have a state with 3 legs. And so you can transform your diagrams into a lot of boxes, a lot of states that are linked, okay?
Yes.
And additionally, FLEXSYMMETRY tells you that you, in fact, the order of the legs and of your states doesn't matter. And this is the idea that all the states behave like vertices in a graph, because in vertices in a graph, there is no difference. There is no ordering of the edges around any vertex. In the usual definition of graph, of course, because you have more involved definition of graphs when this, you can take this into account, but usually you quotient by this order. And this is exactly what FLEXSYMMETRY is doing. It quotient by this order for all those edges. So this is the intuition of, so yes, for me in my mind, this is almost a proof, but it's hard to make it rigorous enough.
It seems like if you don't have any generators with arity larger than 1, then like you get like totally different. Like if your generator just has arity 1 or something, then you can never like split things.
You mean for
like in the free case, if you like the free thing on 1 generator with like arity 1, and you like just say you just have a unit or something.
or if you just have a unit, yes, you will almost not see FLEXSYMMETRY happening because it will just turn it upside down. So
yeah.
Oh, you are speaking about why monoids are equivalent to Frobenius algebras?
I'm just thinking of your conjecture. Well, I'm just thinking out loud. It doesn't really matter. But
Okay, but which conjecture you mean? My conjecture with the labeled graph or the?
yeah, the label graph. Like
Oh, okay.
free FLEXSYMMETRIC category on like a generator with the arity 1.
Okay, yes. So for example, just let's take a unit. So 0 to 1. What is the free FLEXSYMMETRY graphical language? So you have cups, caps, you have swaps. So you have a category of tangles in 4 dimensions. And then what you add is just, you have the right to say that some inputs or outputs are not used because you plug just your generator.
Yeah.
And with FLEXSYMMETRY, you also have something from 1 to 2. So it will be just, I think, some could maybe a partial tangled, say.
Yeah, I guess so.
So this is the kind of thing you would obtain.
And that's a labeled graph in some sense.
Yeah, but my definition of labeled graph, the idea that you have 3 kinds of vertices. You have the input vertices, the output vertices, and you have the generator vertices. And all of them are fixed arity. Input and outputs, they have arity 1, degree 1, and the generators, they have degree the sum of their inputs and outputs.
Okay.
And that's the idea of labeled graph. So a labeled graph is just a graph when you have those generators vertices, those input vertices and output vertices, and you have an order on the input vertices, an order on the output vertices. They should have the good arity, and then you can compose and define.
Okay, this helps me understand your conjecture more. Thank you.
Yeah, the only technical part is because a cap is a graph with 2 vertices which are both inputs. It's just a bone, and both vertices are inputs. So you need to take care of what's happened if you make a loop when you compose. This is a kind of technical.
Any more questions? I've asked like half them, more than half. If not, the remaining people here, we can thank Titouan again.
Thank you for listening to me so long.
Thanks for giving the talk.